Hello all the crazy people out there, my name is Michael, I like wizards and dragons and making games, and it is finally time for me to start making 3D collision videos again, because I said I was going to finish off this series like 4 months ago, and here we are. So if you go down the list in this 3D collision test program here, we've got pretty much all of the basic shapes implemented. We've got collisions with points, spheres, abs, triangles, planes, lines, OBBs. We've got collisions with triangle meshes, calculated in such a way that they're not quite as slow as they could be, although I might still hesitate to call them fast. The only shape which we have not implemented collisions yet with are capsules, and that's going to be the subject of the next few videos. But before I get on to capsules, I want to do a little bit more code maintenance. I want to do a little bit more project maintenance. There's a couple additional helper functions I'd like to write. There's a little bit of code that's already in here that I'd like to rearrange because it'll make our job a little bit less arduous later on. And I guess I'll start with that because that shouldn't take very long. So when I go into the shape ab function, that is the debug draw function. I don't really care about that. And if I scroll all the way down to, where is it? If I scroll all the way down to the bottom by getInterval, there's a list of vertices for the axis line bounding box that's being worked out. And this sort of code is something that's also going to be used when it comes to calculating collisions with capsules, at least the way that I'm going to do them. So I'm going to separate this out into its own accessor method. So we can call the static get vertices, and that's going to be a function. And I'm just going to take this, and we can call that whenever we want the vertices for the axis line bounding box, and I can have the getVertices function return this, and I'm also going to need this, aren't I? The min and max points of the axis line bounding box. And this is just going to be a little helper function that will allow us to quickly and easily get the vertices of an axis line bounding box. Similarly, I'm going to want to be able to get the edges of an ab, so I can write a similar function. We can call the static GetEdges, and that's going to be a function. And that is going to, well, first, vertices, that is going to first get the list of vertices as an array of 8 elements, and then it is going to connect those points to form the 12 edges of an axis line bounding box. That's going to be, connect the 4 points on the top of the ab, the 4 points on the bottom of the ab, and then each of the 4 points top and bottom, you're going to connect them to each other, so, connect the dots. And I could bore you by typing out that entire sequence of 12 edges manually, but instead I'm just going to copy this in for my test program. This is one of those cases where I'd rather just describe the code that I'm writing instead of writing it out the long way, because I know that people get bored and leave when I write out code like this the long way. And it's going to come out looking like this. These are the pairs of vertices that we're connecting. I also rearranged the order of the vertices as they're being returned by an array, because in my test project they were arranged in a slightly different way, and those need to be in a certain order if you want the corresponding vertices to be connecting the correct edges, connecting the correct vertices to form an edge. Likewise, we are doing something similar in the call_OBB class down here. Oh man, that's certainly something down here in the getInterval method for use with the separated axis theorem. And likewise with call_OBB, I'm also going to want to separate this into its own method, like that, because once again, this is going to be something that we're going to be making some use of when it comes to, I'm going to return that, we're going to put a semicolon at the edge of that. We're going to be making some use of this when it comes to checking OBBs versus capsules, and I'm also going to want get edges, and that's going to be its own function. And if I were to go into my test program, is this going to be in the same order? It is not. All right, so let me once again local variable vertices is going to be self.getVertices, and then we're going to return return an array of all of the edges connecting the dots of specific vertices. I'm going to just copy and paste the order of the vertices from my test project just to make sure that it's all in the correct order. So add, sub, add. You can go over that in order if you want. This code is kind of a pain in the neck to read because unlike the axis-aligned bounding box vertices, in which case it's just the extremes of all points, you actually need to do a bit of vector addition and subtraction and multiplication by the orientation matrix to get the points in the correct location. Bit of a pain.
Hey.
So that's going to be the get interval and everything for the AB and the OB. If I were to ABBs and OBBs both use this for checking collisions against triangles, right? So if I were to test this, everything should still be okay. What's triangle? V. Is that going to move the triangle or the point? Good. I want the triangle to stay still. And numpad 2 is AB. We can still detect collisions correctly versus the triangle. Good. And the OB is numpad 7. Can still detect collisions correctly versus the triangle. Like this. So we've just moved some of the code around. We haven't really made any changes to the functionality of this. We're just making it easier for us to access the vertices and the edges of the ABBs and the OBBs later on when we do stuff with capsules. So if I were to simply commit this change, this is a simple one. For neither of those sound like words. Every time I talk about ABBs and OBBs, it sounds like I'm like reciting something from Dr. Seuss or something. Anyway, the next bit of code enhancement that I want to do is going to be going into the line shape, and we are going to scroll down to the bottom, and we're going to write some additional helper functions down here. So we've got the line segment's nearest point, and that's great and everything, but sometimes you might also want to figure out what the nearest connection to another line segment is, and the nearest connection to a array. So instead of just taking an input point and returning the point on the line that's closest to that point, we're going to take an input line or array, and we're going to figure out a connecting line segment, and a connecting call line, which is the shortest possible distance between the line that's calling the method and the input line array. So that's going to look like static nearest connection to array. That's going to be a function which is going to take a array, call array, and farther down, static nearest connection to line. It's going to be a function which takes an input line. And first I'll implement nearest connection to array. I suspect this is going to be by far what takes the most time in this video. This is going to be a lot of math. This is going to be doing a bit of vector addition, subtraction, and all that fun stuff to figure out what the nearest connecting point to array between a line is. It's one of those things that you would think it would be simpler than it is, but it's going to, I believe we're going to be doing something that ends up looking a lot like solving a system of equations, if you remember those from algebra in middle school or high school. So let's get started. So I'm going to just, so I don't drive myself insane, because this is the way it tends to be written out in the mathematical articles on the internet where I learned this code from. I'm going to say var line 1 is going to be self, and var line 2 is going to be the input array. On the surface, this looks like terrible variable names, and it looks like something that's not going to be helpful at all. Line 1 and line 2, but again, in the world of math, this tends to be the way that things like this are written.
Hey.
So first, let's declare a bunch of variables. Let's say var d1 is going to be line1.finish.sub, line1.start. So this is going to be getting a vector from the start of line 1 to the end of line 1. Var d2 is going to be line2.direction. So this is going to basically be the same thing, but for line 2, otherwise known as the ray. So you might want to normalize this d2 vector, but when you construct array in the system, the direction is already being normalized up here in the constructor, and unless you're messing with the values inside these shape structs directly, which you really shouldn't be, this is already going to have a unit length of 1, so I'm just going to leave that as it is. Next, some more variables. Let's say our R is going to be line1.start.sub, line2.origin. This code, by the way, is going to be a special case of some more general code that you might use to find the shortest connecting point between two line-like shapes in space, whether that's a line segment, rays, whatever. So if you're trying to do a similar operation like this for other types of shapes, you might see similar code to this. As you can imagine, as I've been doing for much of the series, when it comes to nearest connection to line, I'm just going to be like using the nearest connection to ray and clamping the value to a maximum distance from the line2.start. Var f is going to be d2. That's a d1. d2 dot against the r. Var next is going to be c is going to be d1 dot against the r. Var b is going to be d1 dot against d2, and let's say var length. That's not a reserved word, is it? Good. Var length is going to be d1 dot against itself. This is essentially the distance of our line segment squared. Let me actually call this length 2. Having the length squared of a value is actually going to make the math a little bit easier. This is less about avoiding a pesky square root operation and more about just because that's what the math is going to demand later on, farther down the line. So, now that we've done some initial setup, getting the directions between certain points that we're measuring, getting the dot products, so the relations between certain angles, we can start to do some actual math. First, we're going to check if this line segment is actually just like a point in space, so if the length of the line segment is 0, if the start and the end points are the same. Special case if the line segment is actually just 2 of the same points. This can be a 2-line comment. So if length 2 is going to be equal to 0. Oh, wait, 1, this is actually misspelled. I was looking at that, and I was trying to find out why it didn't look right. And 2, calling it length 2 kind of actually makes it look like it's the length of line 2, which I don't like, so I'm going to call it actually length squared. Anyway, then we can return new call line from line.start, line1.start, to line2.nearest point on the ray, to line1.start. Okay, so if the start and the end points of our call line are just the same point, then the nearest connecting line to the ray is going to be the nearest point on the ray to the start of the line. Just return a line segment between those 2 points. Okay. Next, I'm going to define a few more variables, or at least, yeah, I'll define a few all up here. 1 is going to be var f1 is going to be 0, var f2 is going to be 0. These will come on to be important later on when we're figuring out, for example, how far along the two line types the nearest points to each other are. And we're also going to want var denominator is going to be equal to length squared minus b times b. As the name implies, we are going to be dividing something by the denominator later on. This is going to be to figure out if the two lines that we're dealing with are parallel. If the two line types that we are dealing with are parallel, then there are infinitely many shortest points between the two lines. That's going to be a bit of another special case. So I can say if denominator equals 0, then we can simply set f1 to 0. It already is 0. It already is 0. Why am I setting it to 0 again? I'll just leave it like that with a comment. If the two... Alright, and as I said, f1 is the distance along the first line where the nearest connection can be found. So setting that to 0 is just going to set it to the line starting point. Otherwise, we can say f1 is going to be equal to clamp the expression b multiplied by f minus c minus 1. All that divided by the denominator. I hate spelling. Anyway, that expression clamped between 0 and 1. So 0 is the starting point, 1 is the ending point. We are going to take this expression divided by the denominator, and that is going to be our f1 point. This is a bit like solving a system of equations, if you remember those from algebra in middle and or high school. So we're going to be trying to minimize, we're going to be taking a system of equations that tries to minimize the distance between these two line type shapes. And once we've figured out our f1, we can figure out our point of interest on line 2. That's going to be f1 multiplied by b plus f. This could come up with an f2 point that is basically behind the origin of the ray. So this is basically trying to figure out the nearest point between a line segment and an infinite line that extends infinitely in both directions. So since a ray does have an origin point, and it does continue infinitely only in one direction, we're going to want to say if f2 happens to be less than 0, we're going to want to set f2 equal to 0, and we're going to want to readjust f1 by saying f1 is going to be a clamp between -c divided by length squared, clamping that between 0 and 1 again. And that will constrain the nearest connecting point to the origin of line 1. And we can return, finally, a new call line that is going to start at line1.start.add d1.mul multiplied by f1. So since f1 is going to be a number between 0 and 1 that represents the distance along the line segment that we are going to have to turn that into an actual value. And then the second point is going to be line2.origin.add d-add has two d's in it, d2.mul by f2. Let's see. That looks good. That looks the same as it is in my test project. So we now have a nearest connection to ray figured out. I should be on another branch, shouldn't I? All right, let me take a moment and let me properly set up the branches on this repository. And lastly, for the nearest connection to line, I tried to be clever about this by just reusing the nearest connection to ray code, but I made a dumb typo in it, and I figured that I would just come back to re-record this bit instead of trying to fix it with annotations or something. So this shouldn't take long. So we can start by turning the incoming line into a ray, with var ray is going to equal new call ray. And the call ray is going to take a starting point of line.start. And it's going to have a direction of line.finish.subtract line.start. And that's going to be a vector which is going to be pointing in the direction of that of the line segment from the start to the finish. If you want, you can normalize this, but it is this vector is going to be normalized when it goes into the call array constructor anyway, so there's not really a point in doing that, unless you just really like to use the normalize method.
Hey.
Next, we can figure out the nearest connection from ourself, from our line to the ray that we've created here. So we can say our nearest connection to ray is going to be self dot basically that, checking the ray that we just created. And since line segments are not infinite in one direction, we're going to need to check the start and the end point to make sure that the connection that we're going with is not like beyond the end of the line segment, and we can do that by saying var starting point is going to be the incoming line dot nearest point to the nearest connection to the connecting line dot start. Var ending point is going to be our self dot nearest point, the nearest connection to the array dot the ending point, the finish, and we can simply return new call line starting point and ending point, so the constrained start and the end points. This code up here, by the way, can be adapted to a number of situations. You can extend it. You can check the start and the end point of the second line as well. If you wanted to simply use this code itself to check the nearest connection between two line segments. If you wanted to check the nearest connection between two arrays, you could, I believe, get rid of, what would it be, this bit up here, and you could instead do something like this to check the to check if f1 is behind the starting point of the first array. It's not perfectly optimal because we are doing a lot of 1 calling this method, and then 2 calling the nearest point method on the line, and then 3 calling the nearest point method on another line. And if you wanted to squeeze out some extra performance out of the system, you probably would want to just copy this code and adapt it from nearest connection to array. I might consider doing that later on down the line when I make some videos on basically micro optimizations that add up in 3D collision systems. But other than that, this should get the job done. I'm going to commit this change, and I'm going to tag this as the week 25 release, and that should be all the additional helper functions that we need to write today. So, next time we'll actually be getting into capsules. I'm going to try to finish off capsules versus all the other basic shapes in the next 2 weeks. And after that, hopefully it won't be like another 3 months before I touch this again. I'd really like to get this finished before like the 2-year anniversary of this series or something. But for now, my name is Michael. I like Wizards and Dragons and making games. I like to make videos on the weirder things you can do in GameMaker, so if any of this sort of weird 3D nonsense appeals to you, feel free to subscribe. I have a Patreon, so if you want to contribute to the channel, links to that can be found in all the usual places. Otherwise, I try to post about 2 game dev videos a week. I hope you all found this useful, and I will see you all later. Special thanks to Army Armbuster, DJ Gibbles, Edward Holt, GameMaker, Harold Guidry, KeyXE, Manta Ray, Maddie Allen, Paul Anstey, Sindra Larson, Squarecrow, The Oz, Vitro V, and Zenjamin for supporting these videos. If you want to contribute to the channel, head on over to the Patreon page down in the video description to join the fun.